Hey guys, our next lesson is again on factoring, but we're specifically going to be talking about factoring what we call monic quadratics. And we'll talk about what that means, so don't worry about that right now. Your prior knowledge is what a quadratic polynomial is, okay? And if you go back to our lesson on introducing polynomials and their anatomy, we called it, you can see the word quadratic refers to degree 2. Okay, so anything that has squared as the highest power of x is what we call quadratic, or whatever the variable is. It doesn't have to be x. Okay, so we're basically talking about anything that's quadratic and learning how to factor those things. Okay? You need to remember what a coefficient is. I just put that there because we're going to talk about that a little bit when we define something. And remember, the coefficient is the number in front of one of the terms of a polynomial. So for example, if I have 3x squared, that's quadratic because it's degree 2, right? And this number in front of a term, remember, that's the coefficient. And then factor, and I'm talking about like the verb to factor. Okay, so the to factor is to break apart into a product. Okay, so break into a product, and that's what we've been focusing on doing for a while here. Okay, so let's go ahead and do your warm-up. Now here's what I want though. I really want you to take a stab at 1, 2, and 3 in your head. Okay, because I think you've done a lot of these enough now where you can probably do these simpler ones in your head. Okay, so I'd really like you to do that. So please work through 1, 2, and 3. Try to do them in your head. And if you really, are unsure, you can go ahead and do it in paper just to check. Okay, and then we'll come together and I'll give you answers, and then we'll do 4 together. Okay, so pause now. Okay, let's check our answers. Well, you'll notice when you do this that we get x squared plus 11x plus 8x plus the last one is 88. And if you notice, we have 11 plus 8. That number and that number are both attached to an x. And so we can say x squared plus 11 plus 8 is 19x plus 88. And then let's just give the other answers. X squared, and we're going to have a 3x and a 9x, so that adds to 12x. And then 3 times 9 is 27, so check that. And this one, these aren't both positive, so our middle thing, we're going to have x squared. We're going to have a 5x and a minus 2x, so that's actually going to bring the 5x down to 3x. And then the 5 times negative 2 is minus 6. Whoops, wrong. Minus 10, excuse me. Okay, now there's a pattern here actually, and that's exactly what we're going to try to utilize, because if you remember, factoring is the reverse of multiplying. So we just multiplied. Now what we're going to do is I'm going to give you ones that look like these orange ones, and you're going to need to break it apart into the factors. So instead of blue to orange, we're going to be going orange to blue today. So number 4 is a pattern that's important actually. Hopefully you recognize something, but I want you to think about the numbers here and how they relate to those two numbers in the end. 11 and 8, how did that relate to 19? And how did the 11 and 8 relate to 88? And then same here, 3 and 9, how do they relate to 12? And how do they relate to 27? And then 5 and negative 2, how did they get the 3, and how did they get the negative 10? So if you think really carefully about that, maybe you've already noticed this, you realize that these two numbers add to make the middle number and multiply to make the last number. And this forms a sort of trick, I guess, we can use for factoring quadratics like this. Okay, so this is going to help you with this. Now you could of course multiply that all out and work with things, but if we go with what we just said, we said the two numbers here add to make that. So if my numbers here are a and b, then what goes here in front of x? Oh, it's a plus b. Now if you are really doing this right, we want to use parentheses because that sum is all in front of x. And then what's the last number? Oh, it's the product of the two, right? So that is actually a really important rule today, and that's what we're going to jump into next and do. We're going to do lots of examples with factoring. This last part in the warm-up we did is so important that you really should have it written down. It's called the sum and product identity. Okay? So if I have x plus a times x plus b, that's always going to multiply out and become quadratic, and it's going to be x squared plus a plus bx, right? We add those numbers to get the middle coefficient, and then plus ab. We multiply the numbers to get the last, it's called the constant term, right? So there's a couple of vocab words we're going to mention real quick before we jump into all of our examples here. So first of all, you realize we called this section factoring monic quadratics. Monic, it's not so important right now, but we're going to talk about monic versus non-monic. Monic basically just means the easy ones. And what I mean by that is the leading coefficient is 1. This easy kind of way that we're going to work with today for factoring is only going to work if it's monic. Okay, so here's what we mean by that. Remember, leading coefficient, leading means the first one, right? So notice this is just x squared plus 3x plus 8. Technically that's 1x squared, right? So this is a coefficient 1. It's called monic. Non-monic, we can just take the same one and just slap a 2 in front of there. That's non-monic anymore. So we're today focusing on monic quadratics. And there's another term that we're talking about today as well, because you might think, well, Mr. Engel, couldn't there maybe be more ways to break these apart if we use decimals and stuff? And yeah, actually that's very true a lot of times. However, today our main focus right now is ones that factor over the integers. And that's a weird way to say that it factors only using integers. Does that make sense? And this capital Z is a weird funky symbol. It's got the little double bar there. And that just is the symbol that means the integers. And again, these two aren't going to come up really prominently, but it is important to kind of know what we're looking for when we say factor, right? And so here's an example. This guy right here, notice that everything here is all an integer. So, and it fits, because remember how we said these two numbers here always add to make that middle, and they multiply to make the end there, right? So x squared plus 5x plus 6 is factorable. It can be factored over the integers, because we can break it into x plus 3 times x plus 2. This, on the other hand, x squared plus 3.5x plus 3, well, even though there's a 0.5 there that's not an integer, maybe there's a way to break it apart with two integers, but actually there's not. The only way this does technically factor x plus 1.5 times x plus 2. The only thing is, not everything here is an integer, right? So we're essentially focusing on ones that just have nice numbers involved, and they only have the leading coefficient being 1, okay? So now we're going to dive into all of our examples. Dive right in. Example number 1. Factor the following quadratics. Okay? Each of these is a monic quadratic. Okay? This leading coefficient is 1, and they're all quadratic because the highest exponent is 2. Okay? So let's go ahead and do this. We got to remember this sum and product identity. Okay? I want you to remember, if I'm trying to factor, what that means is, let me use my regular color here. What that means is I'm trying to break it into a product of two things, right? And I think you and I can both agree that it's going to be an x in the beginning of each of those things here, right? Because the x times x gives me x squared, right? But our goal is to dig out what belongs here and what belongs here. But this rule is really helpful, because if we can figure out two numbers that add to make the middle number and multiply to make the last number, then we've got our two numbers. I want to mention, a lot of you guys are going to pick up on this pretty quick, and you're going to be able to just do these in your head. I love that. If you can factor these in your head, do it. Great. If you're still having a little bit of, or if it's hard for you to think of what numbers are going to work, you can do what I'm about to do here, and that'll help you kind of ease in, and eventually you'll be able to do it in your head without it. So what I like to do is think, well, should I list all possible numbers? Because really it might help me if I find all the numbers that add to 7, all the pairs, right? And then I can choose the one that also multiplies to 12. Does that make sense? But there's a long list of numbers that add to 7. In fact, you could probably think of an infinite number. I mean, if you allow for negatives anyway, right? But if you look at factors of positive 12, that's a pretty doable list. So I kind of like to think of factors of 12 first. So I'm going to take this 12 and write it as, okay, 1 and 12. Let's see, 2, yeah, 2 and 6. 3, yep, 3 times 4. And then next is 4, but I've already got the 4 times the 3. I think I've got all the possible factor pairs of 12 here. So let's just then ask ourselves, I need two numbers that multiply to 12 but add to 7. Can you find a pair of these that does that? Oh yeah, 3 and 4. So it gives me x plus 3 times x plus 4. And there we go, we factored it. So now, you'll notice something interesting. I've chosen all of these on purpose because they have the same constant term. That 12 at the end is the same. And so this list of factors of 12 is still going to be helpful for me in each of these. So why don't we go ahead and finish this off, and then you guys can do the next ones on your own. So they're all going to start like this. And again, we just need to find the factor pair of 12 that also adds, in this case, to 8. Well, that's going to be 6 and 2, or 2 and 6. I'll do 6 and 2. Doesn't really matter. X plus 2 times x plus 6. Doesn't matter if we switch these around. And then the last one needs to add to 13. Oh, good. 12 and 1. So x plus 1 times x plus 12. Okay? So you'll see, even if this number is the same, it's possible to have a different number as the second coefficient and still be factorable. I want you guys to go ahead and repeat the process I just did for these three. So pause right now. Okay. So again, we might start by listing the factor pairs of 18. So that'd be 1 times 18, 2 times 9, 3 times 6, and then 4, no, 5, no, 6. We already got 6 and 3. Okay, I think I've got all the pairs of this as well. So check your answers here. This one should factor into x plus, and I need to add to 11, so that's going to be my 2 and my 9. So you should have x plus 2 times x plus 9, or x plus 9 times x plus 2. That's okay, either way. And then this one should be, we want to add to 9, 3 and 6, so x plus 3 times x plus 6. And then the last one I need to add to 19, and that's going to be my 1 and my 18. Okay, so there's basic examples for this. So far we've only looked at ones that have these numbers all positive. Well, it's possible for those to be negative, and we're going to explore that a little bit now in our next example. So for this one, our instructions are exactly the same, except as I said, we're going to have some negatives involved. Now, I would still suggest a strategy of thinking of this constant term and looking at its factors. Now, if this was positive, we could just list 1 times 40, let's see, 2 times 20, 3, no, 4 times 10, right? I think 5 times 8, let's see, 6, no, 7, we already got 8, okay, I think we've got all of our factor pairs. The only problem is this is negative 40. So 1 times 40 is positive 40, not negative. And here's the thing. I could either have my negative 1 and positive 40 and multiply it at negative 40, but I could also potentially have positive 1 and negative 40. So actually each of these pairs has like a double. So I could put a negative here, or I could have my 1, 2, 4, 5, and then 40, 20, 10, 8, and then those could all be negative. And again, for a lot of us, just running through these in our head, eventually we'll figure out the pair that works. But in the beginning here, you may want to list those out. Okay? So now we can again just address the same question of which of these pairs actually add to make the middle term, the middle coefficient. So we're going to go ahead and start these out in the same way. I'm going to ask that you guys take a stab at this on your own again though. Okay? So please go ahead and pause now, and I want you to finish these off. Okay, let's go ahead and check these out. I need to add to -3. So I gotta figure which ones of these are gonna be 3 away essentially. Now, 1 and 40, 2 and 20, those are like pretty far away. I'm kind of gonna look down here, and if you look, you'll see 5 and -8. So it's gonna be a +5 and a -8. These add to -3, yep, and they multiply to -40. We're good. So let's just quickly go through the answers for the other one. Wait a minute, I can have a -3 here or a +3 here? Well, if you think carefully, that -8 and +5, when they add, make a -3. But if I did a +8 with a -5, and that is this pair, okay? So we used this pair already for A, and this pair is used for B. All we gotta do is switch the sign around for those, and we see that we can get that. And then the last one, we need to add to 6. That's gonna be this one, -4 and +10. So x -4 times x plus 10. Our next couple examples, we're going to consider when is it or isn't it possible to factor something. Sometimes students look at one like this one. I've said, can we factor this? And I'll just tell you right now, the answer is yes. But you look at this one and it kind of seems weird, because if I'm looking for factors of 20 that add to -9, that seems weird, because if I'm listing my factor pairs of 20, I got 1 and 20, 2 times 10, and 4 times 5. And you might be saying, well, Mr. Engel, these are all positive. There's no way those can add to -9. But I kind of misled you a little bit on example 1, and now you need to just think about this and consider it. Is there any way for two numbers to multiply to a positive but still add to a negative? And the answer to that is, oh, actually, Mr. Engel, you're a little bit wrong with our list before. If these are all positive, that works, but what if I make both of them negative? They still multiply to positive 20, but then it's possible for those to add to make a negative. So in the end here, our answer for this one is yes. And in fact, if we look at this, whoops, wrong color. If we look at this, which of these pairs is going to add to -9? This one, -4 minus 5, or plus -5 is -9. So my answer for this is x minus 4 times x minus 5. When you multiply that all out, it's going to become x squared minus 9x plus 20. Now, in our next example, though, I specifically told you they are, oh, by the way, I should have said yes here on the board. I specifically told you these are impossible. And really, these are kind of impossible for the same reason. So I'll probably maybe I won't make part A and B, and I'll just make the same reason for them. The fact is, you can look through these all you want, and there are no factor pairs of 8 that add to 5. There's no factor pairs of 24 that add to -10. And you could certainly try to search through those yourself, but you're going to find out that you're not going to find ones that work, right? So I'll just list that. Okay, there are no factor pairs of the constant that add. Pay careful attention to this wording. Remember, the constant is that last number that doesn't have a variable with it. There are no factor pairs of the constant that add to the middle coefficient. Okay? There are no factor pairs of the constant that add to the middle coefficient. Sometimes we call that middle coefficient, we often say it's the coefficient on x. So I might say that. Okay? So it is important to kind of think about when it is possible or not possible. What we're going to do next is we're going to look at using this factoring method to solve equations involving monic quadratics. So let's look at that next. We've done recently, we've been using factoring and the zero product property to help us solve equations. And that is actually the most important thing for any quadratic equation, is to factor it and then utilize this zero product property. So let's just dive in. If we look at A, x squared plus 5x plus 6 equals 0, it's much easier to solve an equation like this if I have it broken into factors, because then I can figure out, oh, what value for x will make this piece be 0, because then when I multiply it by this piece, it's still just all 0, right? And if you factor this, you should see that this is x plus 3 times x plus 2. And my solutions are then x equals negative 3 or negative 2. And that's it. Okay? So we take the quadratic, we factor it, and then we apply the zero product property to say what the solutions are. Why don't you go ahead and actually do B right now on your own? We'll check your work here for B. When you factor this one, x squared minus 10x minus 24, I think we should find that this is a plus 2 and a minus 12. Because 2 and negative 12 add to negative 10, and they multiply to negative 24. And then if we solve this with the zero product property, oh, x is either equal to negative 2 or positive 12. And there we go. Now, C is interesting because it's easy to jump in and be like, all right, let's factor it. But remember, the zero product property is important because it only works out when you're multiplying to make 0. Well, what's over here? Not 0, right? How can we make 0 be over here? We can take this 24 and subtract it to the other side. So x squared minus 10x minus 24 equals 0. Oh, wait a minute. That's actually the same equation as we did in part B. So we already know this is x equals negative 2 or positive 12 because we already did that work. But the important thing is, remember, if we have a quadratic equation, it is really important you realize we need to use factoring and the zero product property, and we need to move everything over to one side and make it equal to 0. Okay? There's an important thing we'll talk about after these examples, but let's finish off. Okay, x squared plus 8x plus 6 equals 0. In fact, I think that was supposed to be a 16. I had to double check my work, so actually this should be a 16. Well, okay, this one, I chose this one because it's actually interesting for one particular reason. If you think about this, this is actually going to be two numbers that multiply to 16 and add to 8. The only numbers you're going to find is 4 and 4. And that happens to be the exact same number. So this one happens to only have one solution, negative 4. Now you could have also written this or recognized that this was x plus 4 squared equals 0. But even then you're still going to get to the conclusion that x equals negative 4 from that. Okay? So sometimes actually you'll find that we've already talked about ones that don't have a solution, at least not a solution in the integers. But sometimes you'll have just exactly one solution. And then, much of the time, it'll be two solutions. Now, how do we tackle E and F? It's easy to jump in and be like, oh, cool, 0 or negative 12. But be really careful. This is not equal to 0, right? You can only apply that zero product property if that's equal to 0. So what we're going to have to do here is, and it's going to be a little bit of work, but it won't be too bad. We're going to actually add this 20 over there, and we're going to make it x times x plus 12 plus 20 equals 0. So far, so good, right? And the thing is, this still isn't really ready to be factored yet, right? So we're going to actually have to do something here. X squared plus 12x. We're going to actually distribute that in first. Plus 20 equals 0. Now we can ask ourselves if this factors. Can we find things that multiply to 20 and add to 12? I think we can. I think 10 times 2 works. So x plus 10 and x plus 2 equals 0. And therefore my solutions are x equals negative 10 or negative 2. Why don't you go ahead and do F on your own now? Okay, let's look at this one together. If you multiply this out first, or we subtract the 12, it doesn't really matter, we can do that. X plus 1, x plus 2 minus 12 equals 0. And if I multiply this out, it is x squared plus 3x plus 2, and then we still have that minus 12 there. Now 2 minus 12 becomes, I have x squared plus 3x minus 10 equals 0. So again, this took a little bit of work to actually work this all the way through. But then after this, now we're ready to see if this one factors all the way. So, multiply to negative 10 and add to 3. So we're going to have one positive and one negative number, I think, because we got to add to a positive. And I think what we're going to have is x plus 5 times x minus 2. Yeah, because these multiply to negative 10 and then they add to 3, right? And so my solutions for this in the end are x equals negative 5 or positive 2. So there's pretty much everything you need to know about solving equations that are quadratic, monic quadratics. It gets more complicated if we have a different number in front. All right, our final example here is a little bit of a challenge problem that's more for you to do. It says find at least 3 different numbers to fill in that will make this be factorable. And when I say fill in, what I mean is what number could be at the very end here? What could be the constant term? Okay? Now I'll do maybe one with you. I want to remind you guys, or I'll ask you guys the question, what is true if this needs to be factorable, right? I need it to become x plus something or minus, and x plus or minus something else. But the numbers that I'm looking for here, what do they need to do with this 15? They need to add to 15. And then what do they do to make this last number? They multiply, right? So, I don't know, what adds to 15? Let's do 10 and 5. If I do 10 and 5, then 10 times 5 is 50. That works. I want you to find actually 3 more. Remember, this is not something to work together on. This is really something I want you guys to do yourselves, and that means you should have different answers when I check this, right? So go ahead and try this out yourself. Find at least 3 more. And another challenge I want to throw out is, can you work with any negatives? Could you have this one plus and this one minus? You figure out a way to make that work. Anyway, happy math. That's the end of today's lesson, and we'll see you next time.